Have you ever faced like a really complex problem or just this mountain of information
Yeah.
and you just wished for a secret shortcut?
Oh, definitely.
You know, a way to cut through all the noise and just get straight to a smart solution, maybe like a reliable blueprint? We've all been there, I think.
Yeah, absolutely. That feeling of being overwhelmed by complexity,
Yeah.
it's universal, whether you're designing a system, planning a project, whatever.
Exactly. And that feeling, that need for a blueprint, that's actually what we're diving into today.
Hmm.
The fascinating world of design patterns in software development.
Mm-hmm.
Now, hold on, don't let the software development part, throw you off.
Right.
While these ideas did start in programming, what we're really talking about today are kind of universal problem-solving frameworks.
That's a great way to put it.
Our mission then is to sort of unpack what design patterns are, why they're so incredibly powerful, and how understanding them can give you those real aha moments.
Yeah, those moments where it just clicks.
Exactly. Arming you with a toolkit for tackling complex challenges, maybe even way outside coding. Our deep dive into the source material on this, well, it turned up some really fascinating stuff. Trust me, you might start seeing these blueprints everywhere.
Okay, so to really get a handle on design patterns, it helps to first understand the foundation they're built on. That's object-oriented programming, or OOP.
Right, OOP.
At its core, OOP is basically an approach where we wrap up pieces of data and the actions related to that data into these things called objects.
Okay.
And you can think of classes as the blueprints and objects as the actual things you build from those blueprints.
Okay, let's make that solid. The source material had a great example.
Yeah.
Think about your cat, maybe Oscar. Oscar is an object.
A specific instance.
Yeah, exactly. The general idea of cat, that's the class, the blueprint. Every cat has info, like name, age, color. Those are the fields holding its state, right?
Mm-hmm. Its properties.
And all cats do similar things. They breathe, eat, run, meow. Those are the methods, the behaviors. So class is the blueprint, object is the real thing.
Precisely. And this whole way of thinking rests on a few key ideas. One really important one is encapsulation.
Encapsulation, okay.
Think of it like a car engine under the hood. You don't need to mess with the spark plugs or the pistons to drive the car.
Right, you just need the steering wheel and pedals.
Exactly. You have simple interface start button, steering wheel. Encapsulation means an object hides its internal complexity, exposing only what's needed to interact with it. It simplifies things.
Yeah, okay, that makes total sense, hiding the messy bits. And what about polymorphism? That sounds a bit more complicated.
It sounds fancy, but the idea is pretty intuitive. Imagine like an animal show. You have different animals, a cat, a dog, a bird.
Okay.
You just tell each one, make a sound. Now, even if you don't know exactly which animal is next, the cat will meow, the dog will bark, the bird chirps.
Ah, so the program figures out which specific animal it is and does the right sound.
Exactly. Polymorphism is that ability of different objects to respond to the same instruction, the same message, in their own specific way. It's about flexibility.
Got it. Okay, so OOP gives us objects, encapsulation hides complexity, polymorphism gives flexibility. How do design patterns fit in?
Right, so now we can talk patterns.
Yeah.
And it's really important to know what they aren't. A design pattern is not some ready-made code snippet you just copy and paste.
Okay, not a copy-paste job.
No. And it's not a specific algorithm either. It's more like, well, think of it less like a precise cooking recipe and more like a proven architectural blueprint.
A blueprint. Okay, I like that. A blueprint for common challenges.
Exactly. And here's a cool twist from the source material. The whole concept didn't even originate in software.
No kidding. Where then?
Architecture and urban planning, actually. A guy named Christopher Alexander wrote a pattern language. He described recurring solutions to common design problems in buildings and towns, like how high windows should be or how to lay out green spaces.
Wow. Okay, so patterns for building cities.
Yeah, observing what worked consistently. And then that idea was brilliantly adapted to software by 4 authors, Gamma, Helm, Johnson, and Vlisides.
The Gang of 4.
That's them. Their 1994 book, Design Patterns, Elements of Reusable Object-Oriented Software, laid out 23 foundational software patterns.
Okay, so why should you, listening right now, care about these patterns? What's the real value?
Well, the magic, I think, isn't just about writing tidier code, though that's part of it. It's about learning to see the underlying structure of problems.
Structure.
Okay, they are often this toolkit of tried and tested solutions. They teach you how to apply those OOP principles like encapsulation and polymorphism effectively. It's like learning fundamental chess strategy, not just memorizing openings.
So it helps you think better about problems.
Definitely.
Yeah.
And maybe just as important, Patterns give us a common language.
A shared vocabulary.
Exactly. You can be in a meeting and say, oh, let's just use a singleton for that. And hopefully everyone understands the core concept you're suggesting. It makes communication way more efficient.
That's huge, instead of explaining the whole structure from scratch every time.
Right. Saves a lot of time and potential confusion.
Okay, so when we talk about good design software, maybe an organization, even a process, we're usually aiming for two big things, right? Reusability and flexibility.
Spot on. Reusability is about, not constantly reinventing the wheel. Saves time, saves effort, saves money.
Standard stuff.
And flexibility or extensibility is crucial because things always change. New requirements pop up, the market shifts. Your system needs to adapt without breaking.
Change is the only constant, as they say.
Pretty much.
Yeah.
And many design patterns are actually built on a few core principles that really guide you toward that kind of adaptable design.
Okay, principles behind the patterns. What's the first one?
The first big one is encapsulate what varies.
Encapsulate what varies, meaning isolate the bits that are likely to change.
Precisely. The goal is to minimize the ripple effect when something changes. You isolate the parts of your application that you expect might shift from the parts that are likely to stay stable.
The source had a great analogy for this, the ship with watertight compartments.
Oh yeah, that's a good one.
If the ship hits a mine or, encounters some danger, you seal off the damaged compartment, the rest of the ship stays afloat.
Exactly. So in code, if you have, say, tax calculation logic all mixed up inside a method that calculates an order total.
And tax rules change all the time.
Right. You're constantly tinkering with that big method. Instead, you pull out the tax calculation into its own separate encapsulated module or class. Now, tax changes only affect that one spot. Damage contained.
Brilliant. Okay, limit the blast radius of change. What's next?
Next up, program to an interface, not an implementation.
Okay, it sounds a bit more abstract. Interface, not implementation.
It means you should depend on what an object promises it can do, its contract, its interface, rather than how it actually does it internally, its specific implementation.
Why is that important?
Flexibility. It lets you easily swap out different components that fulfill the same contract without messing up the parts of the system that use them.
Oh, okay, like the example of the company class.
Yeah.
Instead of it knowing all the details about a specific program or object.
Yeah, instead of being tightly coupled to programmer.
It just relies on a general employee interface or contract.
Exactly. Then the company doesn't care if it's dealing with a programmer, a designer, a tester. As long as they fulfill the employee contract, the company code works.
So you can add new types of employees later without rewriting the whole company class?
Precisely. It decouples things, makes the system much more adaptable.
Got it. Build flexible connections based on promises, not specific details. What's the third principle?
The third key one is favor composition over inheritance.
Okay, composition over inheritance. I know inheritance is a core OOP thing, like a dog is an animal. Why favor something else?
Well, inheritance seems simple for reusing code, but it can lead to trouble. It creates really tight links between classes.
Tight coupling, right?
Yeah, very tight.
Yeah.
Changes in the parent class can easily break child classes in unexpected ways.
Yeah.
And worse, if you try to add lots of variations, you can end up with this crazy explosion of subclasses. It gets unmanageable fast.
Ah, like the car manufacturer example from the source.
That's the perfect illustration.
If you have cars and trucks with electric or gas engines, manual or autopilot, using inheritance means you need classes like electric truck with autopilot, gas car with manual. It's a nightmare.
A combinatorial explosion. But with composition, which is more of has a relationship, like a car has an engine, you build objects by combining other simpler objects.
Like Lego bricks.
Exactly like Lego bricks. Your car object simply has an engine object, which could be electric or gas, and has a navigation system object, manual or auto. You compose the car from these independent feature objects.
So you can mix and match features easily without creating tons of specialized classes.
Right. It's much more flexible, easier to change and extend. You just swap out the engine brick or the navigation brick.
Okay, those three principles encapsulate what varies. Program to an interface, favor composition, sound like really solid foundations for good design.
They really are. And you'll see them reflected in many of the actual design patterns. So shall we look at a few specific patterns?
Let's do it. The source mentioned they're usually grouped, right? Creational, structural, behavioral.
That's the common categorization based on their primary intent. Creational patterns deal with, well, creating objects smartly.
Makes sense. First one.
Let's start with factory method. The problem it solves is when your code gets too tightly coupled to creating very specific types of objects.
Like the logistics app example. built only for truck objects initially.
Exactly. If it directly creates truck objects everywhere, adding support for ship objects later becomes a huge pain. You have to find and change code all over the place.
So how does factory method help?
You replace those direct creation calls, new truck, with a call to a special factory method. The base class might define a default factory method, but subclasses can override it to produce different types of objects.
Okay. So the main logistics code just asks the factory method for a transport vehicle.
Right. And a road logistics subclass's factory method returns a truck, while a C logistics subclass's factory method returns a ship. But the main code doesn't need to know the difference. It just works with the general transport vehicle interface.
Like the cross-platform UI example too, a main dialog asks its factory method to create a button, and Windows dialog makes a Windows button, web dialog makes an HTML button.
Precisely. The core logic stays clean. It delegates the which specific object to create decision.
Nice. Okay, another creational one. How about singleton? I hear that one mentioned a lot.
Yeah, singleton is common, sometimes controversial, but useful.
Yeah.
The problem, you need to ensure a class has only one instance throughout the entire application.
Why would you want only one?
Often for things like a shared database connection pool, or a central logging service, or maybe application configuration settings. Things where having multiple instances would cause problems or be inefficient.
Okay, a single central point of control or resource. How do you enforce that?
It's usually done with two tricks. First, you make the class's constructor private, so no one else can just create new instances willy-nilly.
Okay, stopped direct creation.
Second, you provide a public static method, often called something like getInstance, that handles creation. The first time it's called, it creates the single instance and saves it. Every subsequent call just returns that same already existing instance.
So everyone goes through that one static method to get the single object.
Exactly. The analogy often used is the government of a country, there's only one, and it serves as a global point of access.
Got it. One instance, globally accessible. Okay, let's move to structural patterns. These are about putting objects together.
Yeah, assembling objects and classes into larger, flexible structures. A really useful one is the adapter pattern.
Adapter, like adapting something to fit.
Exactly. The problem is you have two perfectly good objects, but their interfaces are incompatible. They can't talk to each other directly.
Like the example of a stock market app expecting data in XML format.
Right. But your fancy new third-party analytics library only understands JSON. They speak different languages.
So need a translator.
Precisely. The adapter pattern involves creating a new object, the adapter that sits between the two. It implements the interface that the first object expects, XML in this case, but internally translates the requests and data into the format the second object understands, JSON.
Ooh, just like a travel power plug adapter. My US plug doesn't fit a UK socket, so the adapter bridges the gap.
Perfect analogy. It makes incompatible interfaces work together without changing the original components.
Very clever. Okay, what about the decorator pattern? That sounds interesting.
Decorator tackles the problem of needing to add extra behaviors or responsibilities to objects, but you want to do it dynamically at runtime without modifying the object's original class.
Why not just subclass it?
Well, imagine you have a notification system. You might want to send a basic notification, or one via email or SMS or Facebook or email and SMS, or all three. If you use subclasses for every combination, you get that combinatorial explosion again.
Right. Email notification, SMS notification, email and SMS notification, email and SMS and Facebook notification. Nightmare.
Exactly. So the decorator solution is to wrap the original object, say a basic notifier, with another object, a decorator that has the same interface.
Okay, it looks like the original object from the outside.
Yes. The decorator does its added thing, like sending an SMS, either before or after delegating the call to the object it wraps. And the key is you can stack these wrappers.
Stack them like layers.
Yeah. The analogy is wearing clothes. You start with your basic self, the core object. You can add a shirt, one decorator, then a sweater, another decorator, then a jacket, a third. Each layer adds functionality, and you can combine them flexibly.
So I could wrap my basic notifier with an SMS decorator and then wrap that with an email decorator to get both behaviors?
Precisely. Dynamically adding responsibilities without subclass explosion. Think of adding toppings to ice cream, sprinkle, sauce, whipped cream, or all decorators.
Love it. Okay, finally, behavioral patterns. These are about how objects interact and divide up work.
Right. Algorithms and assignment of responsibilities.
Yeah.
Let's look at the command pattern.
Command, okay.
The problem here often involves decoupling the thing that requests an action, like a button click, from the thing that performs the action, the business logic. It also makes implementing things like undo or do much easier.
Like in a text editor, clicking copy, using the copy menu item, or hitting Ctrl+C should all trigger the same copying logic, right?
Exactly. And you want to be able to undo that copy operation.
So how does command help?
It encapsulates the entire request, all the information needed to perform the action into a standalone command object. This object usually has a single method, like execute.
So clicking the button just creates a copy command object and tells it to execute.
Pretty much. The button doesn't need to know how copying works, just how to create and trigger the command. The menu item does the same. The keyboard shortcut does the same.
Ah, decoupling the trigger from the action and the undo.
Because the command is an object, you can store it, maybe put it on a history stack. To undo, you might have a corresponding unexecute method on the command, or you store the state needed to reverse the action.
Like the restaurant order analogy from the source. The waiter takes your order, creates a command object, the ticket, puts it in the queue, and the chef, the receiver, executes it later. The ticket has all the info.
Exactly. It can be queued, logged, undone. Maybe the chef spoils it and needs to restart.
Makes sense. Okay, last one for today. The strategy pattern.
Strategy is great for situations where you have a class that contains several variations of the same core algorithm, often managed by big if-else or switch statements.
Like the navigation app example. Calculating a route for a car is different from calculating one for walking or biking.
Perfect example. Having one massive calculated route method with complex if, mode else if, gets really messy and hard to maintain.
So what's the strategy?
The strategy pattern says, define a family of algorithms, put each one into its own separate class, the strategy class, all implementing a common interface, like route strategy.
Okay, so you'd have a car strategy, a walking strategy, a bicycle strategy.
Exactly. Then the main class, the context, maybe your navigator app holds a reference to one of these strategy objects. When it needs to calculate a route, it just delegates the work to whichever strategy object it's currently holding.
Ah, so you can easily switch strategies. If the user selects walking, the navigator just points to the walking strategy object and calls its calculate route method.
Precisely. It cleans up the main class immensely and makes it easy to add new strategies later without touching the existing ones. The analogy is choosing how to get to the airport.
Right. You choose your strategy bus, taxi, bike based on factors like cost or time. The goal, get to airport, is the same, but the method differs.
You got it. You swap out the implementation details, the how.
Wow. Okay. We've covered a lot. OOP basics, what patterns are, key principles, and then factory methods, singleton adapter, decorator, command, strategy.
Just a taste, really.
But it really paints a picture. So bringing it back to you, the listener, what does this all mean? It feels like these patterns aren't just abstract code stuff.
Not at all. They're truly universal frameworks for thinking clearly about problems and building solutions that are flexible, maintainable, and, well, reusable.
They give you that common language we talked about and a toolkit so you're not always starting from scratch, reinventing the wheel.
Exactly. And understanding these underlying structures, these frameworks, can seriously sharpen your critical thinking. You start to recognize similar problems and potential solutions everywhere.
Even outside software, like in project management or organizing teams, or maybe even just planning your week.
Absolutely. You start spotting the patterns. Where's the variation? What needs to be encapsulated? Where can I use an adapter or choose a strategy? It changes how you approach complexity.
That feels like the real takeaway. So the next time you hit a really complex problem, maybe don't just jump straight into the weeds. Pause for a second.
Take a step back.
Yeah. Ask yourself, is there a pattern for this kind of challenge? What parts of this problem vary? What parts stay the same? How could I maybe encapsulate those changing bits or delegate a task using something like a command or strategy?
Could the solution blueprint already exist, waiting to be recognized?
Exactly. It's a different way of seeing.
And remember, this deep dive is really just scratching the surface. There are many more patterns out there, all building on these fundamental ideas of good design.
So keep learning. Keep looking for those blueprints in the world around you.
Because once you start seeing them, you'll find that complex problems often become much easier to break down and solve.